Hello, myself Shubhashish Shah, Assistant Professor of Mathematics of Greater Kolkata College of Engineering and Management, GIS School. In this video, I will discuss about Taylor series and Maclaurin series and some of its solved examples. In the previous video, I have already discussed the details of Taylor series and Maclaurin series and infinite forms of these series. So now I will I'll show you some examples of these infinite series. The name of this subject is Mathematics 3, code is BSC301, and this subject is for the students of Computer Science and Engineering and Information Technology. Module number is 1, and this is the syllabus. This is in the syllabus under Maclaurin. Okay. So first example, the question is, we have to expand a function in form of Maclaurin's finite series with Lagrange's form of remainder, and the function is cos x. Okay, so we have to expand this function cos x in form of Maclaurin's finite series with Lagrange's form of remainder. Okay, now for that we have to know the result of the differentiation of this function up to nth order. So first order differentiation of cos x is minus sin x, and that can be written as cos of pi by 2 plus x. F double dash x is minus cos x, and that is equal to cos 2 pi by 2 plus x. So in this way we can write f n x will be cos n pi by 2 plus x. So this is the nth order differentiation of fx, and fn theta x will be cos n pi by 2 plus theta x. These all are required for writing the Maclaurin's series with the form of Lagrange's form of remainder. Okay, now what will be f0? f0 means the value of this function at x equal to 0, and that is 1. Now f dash 0 is the value of the first order differentiation, that is minus sin x at x equal to 0, and that is equal to minus sin x, so this will be 0. So f double dash 0 will be minus 1. So in this way, if double dash 0, so f triple dash 0, that is third order differentiation, will be 0, then f fourth order differentiation will be 1, and so on. Okay, now we know that Maclaurin series is of the form fx equal to f0 plus x f dash 0 plus x square by 2 factorial f double dash 0 plus x n minus 1 by n minus 1 factorial f n minus 1 0 plus rn, and here we are writing this Maclaurin series with Lagrange's form of remainder. So we know that Lagrange's form of remainder after nth term is x to the power n by n factorial to f n theta x. Okay, now just we have to put the values, and we have all the values present in this series. So f0 equal to 1, f dash 0 equal to 0, x square by 2 factorial f double dash 0 is minus 1. So in this way, okay, I write some more terms. F triple dash 0, that is x cube by 3 factorial, into 0 plus x to the power 4 by 4 factorial into 1 plus dot up to x to the power n minus 1 by n minus 1 factorial f of n minus 1 0 plus rn. So rn is x to the power n by n factorial fn theta x. So fn theta x is cos n pi by 2 n pi by 2 plus theta x. Okay. Now, if we just simplify this will be 1 minus x square by 2 plus x to the power 4 by 4 factorial plus dot dot dot. This will be minus, the next term will be minus, plus x to the power n by n factorial, that is the remainder term will be cos n pi by 2 plus theta x. So this is the expansion of the function cos x in the form of Maclaurin series with Lagrange's form of remainder. Okay. Now I'll take the next function sin x. I'll now expand the function sin x. Okay. So like the previous example, we have to first find out the differentiation, result of the differentiation. So first order will be cos x, and that can be written as sin pi by 2 plus x. Next, f double dash x will be minus sin x, and that can be written as sin 2 pi by 2 plus x. And in this way, f n x will be sin n pi by 2 plus x. This is the nth order differentiation of sin x. And we know that fx possesses derivatives of every order for every values of x, and also f n0, that is nth order, the value of nth order differentiation of sin x at x equal to 0 is equal to sin n pi by 2. If we put x equal to 0, this will be sin n pi by 2, which is 0 or plus minus 1 according as n is even or odd. Okay, it can be 0 or it can be plus 1 or it can be minus 1. So it depends on n is even or odd. Okay, so it can be 0 or plus 1 or minus 1. It depends upon n is even or odd. Okay. Now, if we express, if we consider the Lagrange's form of remainder after n terms, then we know that Rn equal to x to the power n by n factorial fn theta x, and this will be equal to x to the power n by n factorial fn nth order differentiation, that is sin n pi by 2 plus and since we are finding the value of nth order differentiation at theta x, so this will be theta x. Okay, so this is the Lagrange's form of remainder where 0 less than theta less than 1. So therefore, mod of Rn, that is mod of x to the power n by n factorial sin n pi by 2 plus theta x. Okay, and this is equal to mod of x to the power n by n factorial into mod of sin n pi by 2 plus theta x, which is less than equal to mod of x to the power n by n factorial. Okay, now we have that sin mod of sin n pi by 2 plus theta x is less than equal to 1, and Rn tends to 0 as n tends to infinity. Since x to the power n by n factorial tends to 0 as n tends to infinity for all x. Okay, so by Maclaurin's infinite series, we get sin x equal to x minus x cube by 3 factorial plus x to the power 5 by 5 factorial minus x to the power 7 by 7 factorial plus up to infinity. This will continue infinitely for all x. Okay, next I'll consider another function, that is e to the power x. Okay, e to the power x. So since we know that the derivative of e to the power x is e to the power x, so nth order differentiation of e to the power x will be e to the power x. Now if we put x equal to 0, and this will be 1. Therefore Rn, there is Lagrange's form of remainder after n terms, is x to the power n by n factorial fn theta x, and that is equal to x to the power n by n factorial e to the power theta x. So since fn x equal to e to the power x, this will be e to the power theta x. Now we know, since e to the power theta x less than e to the power mod x, which is a finite quantity for a given x, and x to the power n by n factorial tends to 0 as n tends to infinity, therefore Rn will tend to 0 as n tend to infinity. Okay, so thus the conditions for Maclaurin's infinite expansion are satisfied, which was this was the condition for Maclaurin's infinite expansion series. Okay, so e to the power x will be equal to 1 plus x square by 2 factorial. We are just putting the values in the general form of Maclaurin's infinite expansion. Okay, so 1 plus x square by 2 factorial plus x cube by 3 factorial plus up to infinite for all x. Okay, so this was the Maclaurin's infinite expansion of e to the power x. Okay, so next function I will take log of 1 plus x fx equal to log 1 plus x to the base e, and the question is we have to expand this function in ascending power of x in an infinite series, and x lies between -1 less than x less than equal to 1. Okay, so we have to expand this series in ascending power of x infinitely in an infinite series. So here fx is log of 1 plus x, so f dash x will be first we have to find the nth order derivative of this function. So f dash x is 1 by 1 plus x, f double dash x is minus 1 by 1 plus x whole square. So f triple dash x will be minus 1 whole square into 2 by 1 plus x whole cube. Okay, so in this way f nx, that is nth order derivative of fx, will be -1 to the power n minus 1. As you see the pattern or sequence, you will see that nth order derivative will be, this is -1 to the power 1, this is -1 to the power 2, so this will be -1 to the power n minus 1 for nth order derivative, into n minus 1 factorial into n minus 1 factorial by 1 plus x whole to the power n. Okay, so this is the nth order derivative of fx. So therefore, if n0, that is the value of the nth order derivative at x equal to 0, will be -1 to the power n minus 1 into n minus 1 factorial by 1, that is this will be -1 to the power n minus 1 into n minus 1 factorial. So if we take Lagrange's form of remainder, that is Rn will be x to the power n by n factorial fn theta x. This is the form of Lagrange's form of remainder in Maclaurin series, infinite series. So this will be equal to x to the power n by n factorial -1, we are putting theta x in place of x, so -1 to the power n minus 1 into n minus 1 factorial by 1 plus theta x whole to the power n. Okay, and it can be written as minus 1 to the power n minus 1, and this is n factorial, this is n minus 1 factorial, so it will be cancelled out and this will be 1 by n, and x by 1 plus theta x, okay, whole to the power n, x by 1 plus theta x whole to the power n. Now when 0 less than equal to x less than equal to 1, then x by 1 plus theta x whole to the power n, that is this term, will tend to 0. If x lies between 0 and 1, and this will tend to 0 as n tends to infinity. What is the reason? Since x by 1 plus theta x, since x by 1 plus theta x is a positive term and it is less than positive term and it is less than 1. So this will x by 1 plus theta x whole to the power n will tend to 0 as n tends to infinity. And also we can see that 1 by n tends to 0 as n tends to infinity. So finally we can conclude that Rn tends to 0 as n tends to infinity. Okay, so this is a point number A. Now the another conclusion we can conclude that, okay, I am writing here. So the another conclusion I can conclude that when, depending upon the values of x, when minus 1 less than x less than 0, when x lies between minus 1 and 0, then x by 1 plus theta x may not be numerically less than 1. Okay, if x lies between minus 1 and 0. So this term, this is not mandatory that x by 1 plus theta x will be greater than 1. So this may not be numerically less than 1, and therefore we can say that x by 1 plus theta x may not tend to 0 as n tend to infinity, which happened in the first case. If x lies between this interval, this is not happening. Okay, this may not happen. Thus, we cannot get any definite conclusion from Lagrange's form of remainder. So, in this case, we use Cauchy's form of remainder. So, in the first case, we are getting seeing that the Lagrange's form, the condition of Lagrange's form of remainder is satisfied. But in this case, we are not getting any conclusion from Lagrange's form of remainder. So we have to use Cauchy's form of remainder, and which is Rn. Cauchy's form of remainder, Rn equal to x to the power n into 1 minus theta whole to the power n minus 1 by n minus 1 factorial into Fn theta x. And these all forms have been discussed in my previous video. You have to study this, otherwise you will not understand this solution of this problem. Okay, so this will be equal to x to the power n into 1 minus theta whole to the power n minus 1 by n minus 1 factorial, and Fn theta x will be minus 1 to the power n minus 1. I have already found out the value of nth order derivative of fx. So Fn theta x will be minus 1 to the power n minus 1 into, okay, I need to change the pen. So n minus 1 factorial by 1 plus theta x whole to the power n. And okay, so this is equal to minus 1 to the power n minus 1. If we simplify this, x to the power n by this x to the power n by 1 plus theta x into 1 minus theta by 1 plus theta x whole to the power n minus 1. So this is 1 plus theta x whole to the power n minus 1 into 1 plus theta x, that is 1 plus theta x whole to the power n. Okay, and this is 1 minus theta whole to the power n minus 1, and n minus 1 factorial is cancelling out. So by simplifying, I have written this. So now 1 minus theta by 1 plus theta x, this term, okay, is positive, and this is less than 1, positive and less than 1. Hence we can say that 1 minus theta by 1 plus theta x whole to the power n minus 1 tends to 0 as n tends to infinity. Okay, since this is positive and less than 1. Okay, also we can say that x to the power n tends to 0 as n tends to infinity. What is the reason? Since x lies between minus 1 and 0. So 1 by 1 plus theta x is bounded, and hence we can say that Rn tends to 0 as n tends to infinity. Thus here the conditions of Maclaurin's infinite series are satisfied, and we can now write the Maclaurin series infinitely, which is fx equal to f0 plus x. Okay, I write the upper portion. Fx equal to f0 plus x f dash 0 plus x square by 2 factorial f double dash 0 up to, this will continue infinitely. So fx is here log of 1 plus x to the base e, and f0 will be x, plus, sorry, minus x square, sorry, not f0 equal to x, f0 will be 0 if we put the values. F dash 0 is 1, so x, this will be x minus x square by 2. Just put the values from the previous findings, then you will get this series x cubed by 3 minus x to the power 5 by 5 plus up to infinite. So where minus 1 less than x less than equal to 1. Okay, so this is the expansion, infinite expansion of the function log of 1 plus x to the base e. Next question is, show that a to the power x equal to 1 plus x log a plus x square by 2 factorial log a whole square plus dot 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 plus x to the power n minus 1 by n minus 1 factorial log a whole to the power n minus 1 plus x to the power n by n factorial a to the power theta x log a whole to the power n. Okay, so we'll use the Maclaurin's series expansion to prove this. So we know that Maclaurin series is fx is equal to f0 plus x f dash 0 plus x square by 2 factorial f double dash 0 plus x cubed by 3 factorial f triple dash 0 plus x to the power n minus 1 by n minus 1 factorial f of n minus 1 0 plus Rn, where Rn is equal to x to the power n by n factorial fn theta x. We have taken the Lagrange's form of remainder, okay, where 0 is less than theta less than 1, theta lies between 0 and 1. So now just we have to find these values and put in this expansion, then I think we'll prove this. Okay, so for that the function is fx is a to the power x, so for that we have to find the derivative of the nth order as well as first order, second order, as well as up to nth order. Okay, so if fx equal to a to the power x, then f dashed x is equal to a to the power x log a. You know, f double dashed x will be a to the power x log a whole square f triple dashed x will be a to the power x log a whole cube like this, and the nth order derivative will be a to the power x log a whole to the power n. Okay. Now what will be fn theta x? Fn theta x will be a to the power theta x log a whole to the power n. Just we have put theta x in place of x. Okay. Now what will be f0? F0 is a to the power 0, that is 1. Okay, so f dash 0, f dashed 0, f dashed 0 will be log a, f double dashed 0 will be log a whole square, and so on, and f n minus 1 0 will be log a whole to the power n minus 1. Now see, we have found out all the required values which have to be put in this series. Now if we put these values in this series, then what will happen? fx is a to the power x equal to f0, so f0 is 1 plus x into f dashed 0, f dashed 0 is log a, so x into log a plus x square by 2 factorial, x square by 2 factorial, f double dash 0, f double dash 0 is log a whole square, plus, in this way if we continue, this term will be x to the power n minus 1 by n minus 1 factorial, f of n minus 1 0 is log a whole to the power n minus 1, and plus the remainder term. So the remainder term is x to the power n by n factorial, x to the power n by n factorial, f of n minus 1, fn theta x, fn theta x. So fn theta x we have found out where this is fn theta x. So fn theta x is a to the power theta x log a whole to the power n. Now see that the required result we have to prove it has come. Okay, so hence the proof. So these were all for this video. In this video, so I have discussed, I have solved some problems of Maclaurin series and Taylor series, and they are for their infinite forms. So you have to solve, you have to practice this type of sums. And if you face any problem, or if you have any query regarding these chapters and problems of this chapter, then you can contact with me. My contact details is given in the first slide of this video. Thank you.